It's half as high as this one. So right there, we have a pretty good graph of y equals 2 to the x. Okay? Now, we're going to take that graph, but we're going to say, okay, I don't want y equals 2 to the x. Really, what I want is, I want my principal versus time. So here's my principal, here's my time, and I want my graph to represent P equals, it's $8,000, times 1.01 to the 4t, the principal function that applies to this situation. How do we do that? I don't have to make a new graph. I just leave off my x here and my y here, and I don't label these points. I don't label this 1, 2, or -1, -2. What I do is, I notice that between here and here, this graph doubles. Well, in the case of this function, the doubling time is about 18 years. Now, it's a little more precise than that, and you'd actually want to use the accurate numbers, but let's just get the flavor of this by saying, okay, we got 18 here, 36 here, and then, of course, here's 0. Well, this must be -18, this must be -36. Okay? Now, how do I know I get 36 and -18, -36? I can accept that the doubling time is 18, so that this doubles between here and here. Well, between here and here is the same distance as between here and here, if you did the graph accurately. So this is 18 years, this is 18 years. Okay, I had people labeling 18, and I think somebody labeled 20 and 22. So you're thinking, but not quite right. Intervals are equal, so the difference between here and here has to be the same as the difference between here and here. Also, the difference from here to here has to be the same as from here to here, so this must be -18, because this is certainly 0, and this similarly has to be -36. Then, our y scale, and I'll just, draw a little line here, this has to be our t equals 0 value, which is $8,000. At t equals 0, we do have $8,000, because 1.01 to the 4t would be 1.01 to the 4 times 0. That's 1.01 to the 0. And as I said in class, I certainly hope, and I'm just looking here to see if that's even visible at the top of the screen. I'm going to zoom back just a little bit, because sometimes software doesn't represent the top of the screen very well. Okay. If 1.01 to the 0, as I was saying, is, if you think it's 0, you're going to lose all your money really fast, right? Okay? It's not, as soon as you plug into this function, you got 0, and then you're going to have to go to the bank and convince whoever did that they're wrong. And since they probably don't understand mathematics very well, they just have tables and formulas and computer programs, you're going to have to go up the ladder until you convince somebody that you should really have your money, okay? Because 1.01 to the 0 isn't 0, it's 1, meaning that you really have the $8,000 that you started with. It doesn't immediately go to 0 when t is 0. Okay, well, in any case, when t is 0, 1.01 to the 0 gives you 1, I almost said 0, and that's $8,000. So when t equals 0, you've got $8,000. Okay? Well, this distance is equal to this distance, so that from here to here is $8,000. From here to here has to be another $8,000, meaning that you have your $16,000 here. And from here to here is another $8,000. Well, that's going to give you $24,000. And from here to here is another $8,000. That gives you $32,000. So that after 18 years, you've got 16,000. After 36 years, you've got 32,000. And somewhere between here and here, you've got your 24,000. So you could say, okay, well, I'll just go over to here and see when I get my 24,000. It's going to be between 18 and 36, kind of close to halfway, but closer to 18 than 36, because this graph kind of dips down here between here and here. It's concave upwards, and that gives you, that has an effect, okay? If it was a straight line from here to here, then 24,000 would intercept that straight line halfway between 18 and 36. But it doesn't. And I'm not even sure I said that right. I'm not going to say any more about it, because we're going to investigate that whole phenomenon. Okay? Now, if you want to know when you have $100,000, how would you do that? Well, you know, every time you go 18 years, your principal is going to double, isn't it? So if you go another 18 years, you're going to double what you have at the 36-year mark. That'll give you $72,000 at the next mark. Of course, that's going to be after 54 years. And after another 18 years, you'll double that, you'll have $144,000. That's at 72 years after you started. Now, if this is an investment somebody made for you at birth, or maybe made previous to your birth, then you're going to be somewhere in your 60s when you finally hit $100,000. And hopefully your $100,000 will be worth something at that time, because it's hard to predict that far in the future. This model, and I'm pointing to this model, but it's the same as this one, also tells you that maybe this investment was made for you 36 years earlier, maybe by a grandparent. They invested how much money at this point to get you up to $8,000 at this point? Well, every 18 years the investment doubles, means if you go back in time, every 18 years, it will have been worth half as much. So you have $8,000 here, you go back here, you have half as much, that's $4,000. You go back here, you have half of that, which is $2,000. Somebody that invested $2,000 36 years before you were born at a guaranteed 4% annual interest, compounded 4 times a year, will get you to about this at birth and get you out here later than your birth. Now, if that 18 isn't accurate, if it's really 17 and a half, then maybe it doesn't take till you're 72. Maybe you get it when you're 70. Okay? You can figure out what the exact doubling time is and adjust the graph and the labeling of the graph accordingly. These numbers aren't going to change, but these could change, and these would change if you did this precisely.